Greetings and welcome to lesson on equations and inequalities, specifically linear inequalities. Let's run through the objectives for this lesson. First thing, we need to talk about vocabulary. We need to be able to speak the same language, walk the walk, talk the talk, and so we'll run through some vocabulary. Next, we'll solve and graph linear inequalities, as well as compound inequalities, and polynomial rational inequalities using some test points. So what does an inequality look like? Well, it looks like an equation, but instead of an equal sign, we have some inequality symbol like less than or equal to, greater than or equal to. If it has an equal sign, it's no longer an inequality, it's an equation. Let's talk some definitions here. An inequality is a statement that one algebraic expression is less than or equal to, greater than or equal to another algebraic expression. The domain of an inequality, the domain of the variable of an inequality is all sets of real numbers where both sides of the inequality is defined. The domain really here is no different than the domain of an equation. It just means if you have a denominator, you got to watch out for that denominator to be 0. If you have a square root, you got to be careful that that square root inside that square root is not negative. So the domain is all the values of x that it can be, and it doesn't set off something that's undefined. Solutions. Hey, the solutions to the inequality is just those real numbers that make the left-hand side a true statement with the right-hand side. So the whole entire statement has to be true. For example, 5 is less than 2 is a false statement. Therefore, whatever number we put in for x was not a solution. So the whole entire inequality must make a true statement. Well, to solve an inequality just means to find all the solutions of the inequality, that is the solution set. Solution sets are intervals. We frequently will graph the solution sets for inequalities in one variable on a number line. So for example, the graph of an inequality, x is less than 5, is the interval from -infinity all the way up to 5. But because there is no equal to, we put a parenthesis around the 5 because we are not including it. One way of showing it is graphically, where we have the parenthesis on the 5 and everything less than 5. Another way of showing it is in this interval notation where it's parenthesis, -infinity, 5, parenthesis. A conditional inequality such as x is less than 5 has its domain, which is at least one solution and at least one number that is not a solution. Here's an example. When x is 4, x is less than 5. 4 is in the domain of x. Now let's try x equals 6. 6 is not less than 5, and that's at least one number that is not a solution. That's what it means to be conditional inequality. An inconsistent inequality is one which no real number satisfies it. You would get a result after you do the math. You would get something like 2 is less than 1, and all the x's, all the variables drop out. Well, that's an inconsistent equality because there's no value of x that can force that to be true. And then the identity is one of those inequalities that is actually satisfied by any value of x. You can throw any value in there and you're still going to get something like 2 is less than 4. And that is always true no matter what x is. The x's kind of drop out in that sense. All right, a non-negative identity. That's where x squared is greater than or equal to 0 for any real number of x. It's because x squared is x times x. And either you have one of these three cases. One, you either have two positive values, so if x is 2, you have 2 times 2, which positive times positive is a positive. You either have two negatives, -2 times -2 is a positive value, or 3, you have two zeros. 0 times 0 is 0. So this is the non-negative identity. There is never a negative or is non-negative. It's always non-negative. Still working with some definitions here. Equivalent inequalities. Well, let me take a step back. When you had equivalent fractions, they may not have looked the same, but in essence on a number line, they sat in the same place as the number line. For example, 1/2 and 2/4. If you put those on a number line, they sit in the number line exactly the same. Same position on the number line. Although they don't look the same, they are equivalent fractions. Well, we have equivalent inequalities when the two inequalities have the same exact solution set. They are called equivalent inequalities. The following operations always produce the equivalent inequalities. Simplifying one or both sides of an inequality by combining like terms and eliminating parentheses. You'll kind of get something that looks the same. Secondly, adding or subtracting the same expression on both sides of an inequality will also cause equivalent inequalities. It's very similar to what we do with equations. You know, when you have x plus 1 equals 5, you get to say -1 minus 1, and everything holds true. That's the same rules as we have for equivalent inequalities. Now, the rules are pretty much the same for equivalent inequalities when we're multiplying each side of the inequality, very similar to when we deal with equalities. We will run into a little slight difference, though. So let's run through this at first. Let's say C represents some real number, and we're saying that A is less than B, our symbol is less than, and we're going to give you an example of 3x is less than 12. Here's the thing. If we multiply both sides of the inequality by C, for example, 1/3 times 3x is less than 1/3 times 12, the symbol does not change. Now I'm going to give you numbers because sometimes it's easier to see with numbers what's going on. I'm going to say 2 is less than 10. That's a true statement. I'm going to say A is 2 and B is 10, and that's a true statement. And now I'm going to multiply 3 to both sides. 2 times 3 is 6. 10 times 3 is 30. 6 is still less than 30. So multiplying by the same value to each side, as long as it's a positive number, the statement still holds true. Likewise, when we divide by that value, so let me take that 6 and 30 and divide it by 3. So 6 is less than 30, and if I divide each side by 3, I get 2 is less than 10, still holds true, and our symbol is unchanged. But here's where the change comes. But when we multiply by a negative number, our sign reverses. It changes. So remember that 2 times -3 is not less than 10 times -3. We have to switch the order, reverse the symbol to make it a true statement. So now we have 2 times -3 is -6 is greater than -30. So we have to flip that symbol. And this goes along with when we are solving for inequalities. Anytime that we multiply, and it also applies to division, when we apply division of a negative number, we also have to flip that symbol from a positive, a less than to a greater than, or a greater than to a less than. It gets flipped. An inequality in one variable looks like this. AX plus B is less than 0, or AX plus B is less than or equal to 0, where A and B represent real numbers and A does not equal 0. If A equals 0, the X would go away and that would be a boring statement. So we want A to be a non-zero number. Now, I focused on less than and less than or equal to, but it also applies to greater than and greater than or equal to. Let's work through a handful of examples. We're going to solve each of these inequalities. We're going to graph the solution as well as state it in an interval notation. So let's start with A. 2x is less than -2. Now, 2x is less than -2. I'm going to divide each side by 2, but 2 is a positive number, so I don't flip the symbol at all, and I get 2 is less than -1. So because we're not including -1, we do a parenthesis and we put it to the left. And a cool little trick, little hint, is if your x is on the left, the arrow will point in the direction your arrow on the number line needs to go. It's just a little helpful hint that as long as your x is on the left, the symbol will point to the direction which your line needs to go. So our solution set is x such that x is all values less than 1. That's in set notation. In interval notation, it's going to be -infinity to 1, but not including 1. Let's look at B. 7x minus 11 is less than 2 times x minus 3. Now, ultimately, we're going to go ahead and start solving for x. I've decided to add 11 to both sides. We get 7x equals 2x plus 5 because 2x times -6, -6 plus 11 is +5. I'm going to get rid of this 2x by subtracting 2x from both sides. Adding and subtracting will have no effect on the symbol whatsoever. It's only when you divide or multiply by a negative number which you will change the symbol. But adding and subtracting has no effect to the symbol itself. So subtracting 2x from both sides, we get 5x is less than 5, dividing by 5, x is less than 1. Now we're not including 1, so graphically we're going to have a parenthesis. Also set or interval notation will have a parenthesis. Our set notation is x such that x is less than 1. Our interval notation is -infinity to 1, but don't include it because that's a parenthesis. And again, this little arrow will help me figure out which arrow am I going to go to the left or to the right. This is pointing to the left, so it's a parenthesis at 1 and drag your arrow all the way to the left. All right, the third example in this set, we have x minus 3x is greater than or equal to 2. I'm going to go ahead and subtract 8 from both sides. And we get -3x is greater than or equal to -6. Now in this next step, I'm going to divide by a negative number. That means when I divide by a negative number, I must change the direction of this symbol. So it's no longer greater than or equal to, it's less than or equal to. And I have x is less than or equal to 2. Now our set is all values of x such that x is less than or equal to 2. Because we are including 2, we have a bracket on our interval notation. So from -infinity to 2, including 2. Likewise, this bracket is also included in our graph of our solution. So graph of our solution, our arrow is heading to the left, and therefore we draw our arrow to the left. As a reminder, when dividing or multiplying each side of the inequality by a negative number, you must flip that inequality symbol. All right, let's run through another example, calculating the results of the Bermuda triangle experiment. Now I'll let you read through this problem description. Just pause the video. Hopefully it's sharp enough to where you can see it. But as I move on, let's grab the most important part to actually do our math. Number 1, the plane is 150 miles along its path from Miami to Bermuda. It's cruising at 300 miles per hour when it notifies the tower that it's now set on automatic pilot. The entire trip from Miami to Bermuda is 1,035 miles. We want to determine how much time should we let pass before we, let's say we're the tower, become concerned that the plane has encountered trouble. Let's let t be the time elapsed since the plane is on autopilot. Well, then 300, that's the speed at which the plane is flying. So the rate times the time will be the distance the plane has flown in that many hours. The distance the plane has already flown from Miami is 150, and then plus the distance that it's going to fly on autopilot is the 300 times t. Now we know the plane's distance from Miami is greater than or equal to the distance from Miami to Bermuda. If it's greater than that distance, they are in trouble. They have passed up Bermuda. So if the plane's ultimate distance, its final distance, is greater than or equal to the distance from Miami to Bermuda, we know the plane could be in trouble. So the plane's distance from Miami, that's going to be 150 plus 300t. The distance from Miami to Bermuda is the total distance of 1,035 miles. We have our inequality that we can solve. We're going to subtract 150 from both sides. We're going to now have 300t is greater than or equal to 885 miles. Let's divide each side by 300. 300 is a positive value, so we leave the sign alone. And we get t is greater than or equal to 2.95, which adds about 3. So us up in the tower, if we don't hear from the plane in 3 hours, we're going to assume they are in trouble. And we may have to reach out to them with a search party or something. But about 3 hours, then we'll suspect there's some trouble there. Well, that was a little bit fun where we could see how inequalities can be applied to a real life problem. Now let's get back to the general statements of inequalities. And we have a couple of inequalities we want to find the solution set. So let's take A. So I've got a lot going on here. I'm going to distribute the 7, and then I'm going to add like terms, distribute the 3, and if I can add like terms, that would be great. So I get 7x times plus 14 minus 20 minus 4x is less than 3x minus 3. Adding like terms, I get 3x minus 6 is less than 3x minus 3. We get negative 6 is less than negative 3, okay, after we subtract 3x from both sides. Now, is that a true statement? Absolutely. Negative 6 is less than negative 3. And in fact, any value of x will make this true. If x is 10, that's going to be 30 minus 6, 30 minus 3. It's still a statement that's true. So in fact, this is always true. So the solution set is negative infinity to positive infinity. Any real number will make that statement true. All right, let's look at part B. 2 times x plus 5 plus 3x is less than 5 times x minus 1 plus 3. I'm going to do the same strategy where I'm going to distribute for both sides, and then I'll add like terms and see what I get. 2x plus 10 plus 3x is less than 5x minus 5 plus 3. Adding like terms, we get 5x plus 10 is less than 5x minus 2. And we end up with 10 is less than negative 2. Now, is 10 less than negative 2? No, that's a false statement. And in terms, there is no value of x that can ever make this statement true. And therefore, there is no value in x. And then the inequality has an empty set for its solution. All right, so now let's look at compound inequalities, and specifically compound with an OR statement. First and foremost, an OR means one or both can be true at any one time. So one or both can be true at any one time. They don't both have to be true at the same time. It's just one of them has to be true at any particular time, or any particular value of x. So we have x, 2x. 2x plus 7 is less than or equal to 1, or 3x minus 2 is less than 4 times x minus 1. And so let's take these one at a time. I'm going to run through these. Moving the 7 over, subtracting 7 from both sides, we get 2x is less than or equal to negative 6, dividing by 3. Positive number, so we don't touch the sign. x is less than or equal to -3. That's one solution. Working with our other part of our inequality, we get 3x minus 2 is less than 4x minus 4. Moving the 4 to the right and the 2 to the left, we get negative x is less than -2. At this point, I have to divide by a -1. That means this symbol has to flip. And we get x is greater than 2. Now it's time to graph our solution. We have one that x is less than or equal to 3, so our line will be going to the left. And for this solution, our line is pointing to the right, and that's perfectly fine with an OR. Here we go. So x is less than or equal to -3. We have a bracket, and our arrow goes to the left. For x is greater than 2, it's a parenthesis, and our arrow goes to the right. And in essence, if I put the first graph on top of the second graph, that will be my solution to my full OR inequality. So we have something pointing out each direction, and that is perfectly fine with an OR. Only one of these things has to be true at any one time. And our answer in our solution set in interval notation will be -infinity to -3, including it, union with not including 2, but up to infinity. Now let's look at an OR AND statement. I'm not going to run through this step by step because I think solving it, you probably get an idea of what's going on here, but I'll walk through it very quickly. So we have two inequalities with compounded with the word AND. 2 times x minus 3 plus 5 is less than 9, and 3 times 1 minus x minus 2 is less than or equal to 7. When you go through the process to solve for inequalities, you will get x is less than 5 and x is greater than or equal to -2. Remember, for the other one, I had to flip the symbol in the process. Now here's what we have. X is less than 5. I'm not including 5, but it goes to the left. X is greater than or equal to -2. I do include -2 and I go to the right. And because it is an AND, both of these statements must be true at the same exact time. It's this and this. It's not an OR where either one of these can be true. They both must be true at the same exact time. So if I laid one of these graphs on top of the other graph, it's where they overlap is what's going to be my solution. So only from -2 to the 5, but not including the 5, everything in between is where it overlapped. And therefore, my set interval is from -2 to +5. Now, another way of looking at an AND inequality is where you have a compound inequality where there are 3 parts to it. For example, -5x, here we go, -5x is less than 2x plus 3 is less than or equal to 9. This is a compound inequality with an AND because it's this and it's this. So this is another way of viewing an AND. There's 2 ways of solving this type of compound inequality. The first way is to, well, solve them separately. Break them up. It's going to be -5x is less than 2x plus 3. That will be one inequality. And the other inequality will be 2x plus 3 is less than or equal to 9. So we'll break them up into 2 and we'll solve these separately. Solving the first one, I'm going to subtract 3 from both sides, and then I'm going to divide by 2, and I get -4 is less than x. Now I don't want to graph this as it is because my x is on the right, and this is not my little cheat here. If the x was on the left, it would be my little cheat. Okay? Secondly, 2x plus 3 is less than or equal to 9. Let's go ahead and solve for the inequality of x here. Subtract 3 from both sides. We get 2x equals less than or equal to 6. Divide by 2. X is less than or equal to 3. Now, both of these things must be true. So since x is in the middle, let's just push those two things together. And we get negative 4 is less than x is less than or equal to 3. So this is kind of the neat way of crunching them together. And I like to think of it as x in the middle, and therefore you will only have the middle portion, which will be on your graph. It has from this low number to this high number. It's going to be kind of in the middle and only in that middle. For set notation, it's going to be x such that negative 4 is less than x is less than or equal to 3. For interval notation, it's going to be negative 4 to 3, including 3. And for graph solution, it's going to be parenthesis on the 4, line all the way up to the 3 with a bracket. Now that was our first option. Break it apart, solve them separately, and then bring the answers together. How I like to do it is I like to solve them simultaneously, which means I just leave it as it is, but I just have to remember what I do to one side, I do to all sides, left, middle, and right. All right, so I'm going to leave it as is. Negative 5 is less than 2x plus 3 is less than 9. I'm going to subtract 3 from all three sides, left, middle, and right. Now I have negative 8 is less than 2x is less than or equal to 6. Now the next thing I have to do to get x all by itself is to divide by 2. But if I divide the middle by 2, I have to divide the left and the right by 2 as well. So let's divide everything by 2, and we get negative 4 is less than x is less than or equal to 3. Same answer, but that was working on both of the problems at the same time by working on the left, middle, and right at the same time. I actually like this method, and then I can see my range of values is going to be this boundary range. It's not going to go all the way off to infinity. It's not going to be off to infinity that way. It's this bounded range because x is in the middle. Same solution graphically, same solution set, and interval notation. Now let's take a look at a different kind of an example where we're going to find the interval of our values for a linear expression. And in fact, we're already given the solution is negative 2 is less than x is less than 5. X can only be in this range. And if x can only be in this range, let's find real numbers a and b. So a is less than 3x minus 1 is less than b is a true statement. Now we know x can range from negative 2 to 5. So let's start there. Taking what I know about 3x, if I multiply this x in the middle, I would have to multiply both the left and the right by 3. And I get negative 6 is less than 3x is less than 15. All right, I'm almost there. I just have to subtract 1 in the middle. And if I subtract 1 in the middle, I have to also subtract 1 from the left and the right. So I get negative 7 is less than 3x minus 1 is less than 14. Since this is the situation I wanted to end up in, I know A is negative 7 and B is 14. Well, let's try a similar problem than the previous problem, but this time a real-world problem. Now we know the temperature in London can range from 10 Celsius to 20 Celsius during this 3-week period of time you'll be working there. You want to decide, well, what kind of clothes that you want to bring. I mean, if 10 degrees Celsius is cold, you better bring a jacket. If 10 degrees Celsius is warm, then you don't need a jacket. So we want to be able to convert this 10 degree to 20 degrees Celsius over to Fahrenheit. We do know what that calculation of conversion is. Fahrenheit equals 9/5 C plus 32. We want to know what range of Fahrenheit is that in London while you're staying. Now let's start off with what we know. We know our temperature conversion from Fahrenheit to Celsius. We also know the degrees for those 3 weeks under consideration is from 10 degrees Celsius is less than or equal to Celsius is less than or equal to 20. We know it's in this range. Very similar to what we did in the last problem, we're going to break apart the F equals and turn this C into 9/5 C plus 32, and then we can replace it with an F. So first things first, I need to multiply both sides by 9/5, or all three sides by 9/5. 9/5 times 10 is less than or equal to 9/5 C is less than or equal to 9/5 times 20. The good news is 5 and 10 reduce, so I got 9 times 2 is 18, and 5 and 20 reduce, so that's 9 times 4, which is 36. So we have 18 is less than or equal to 9/5 C is less than or equal to 36. Now the next step we need to do is add 32 to the middle, the left, and the right. And once we do that, we know that 50 is less than or equal to 9/5 C plus 32 is less than or equal to 68. But the cool part about this is we know 9/5 C plus 32 is just a very, very fancy way of writing Fahrenheit. Therefore, when you travel to London and the temperature is between 10 and 20 degrees Celsius, it will be between 50 and 68 degrees Fahrenheit. You're going to need a sweater. Let's look at how to solve an inequality by using this point method. The first step is to rewrite, if necessary, the inequality so that the right hand of the inequality is 0. And then you're going to simplify the left-hand side as best as possible. Second, you're going to factor the left-hand side. Third, you're going to draw a number line and find the plot points where each factor is 0. The endpoints obtained divide the number line into n plus 1 points. So if we factor it and we have x is 3 and x is 5, that's endpoints, but it divides up the number line into 3 different regions. Step 4. The final expression on the left-hand side of the inequality in step 1 is always positive or always negative for any of the regions or intervals that we found in step 3. We're just going to find some point in that region to test. Once we find that test point, we're going to put it into our original equation and figure out, was it positive or negative. If that test point is positive, in that whole region will be positive values. If the test point came out negative, that whole entire region will be negative. And we're going to float that on a number line. And then from the sign chart, we're going to set up our solution. I think seeing this is going to be a lot easier than putting it in words and trying to describe it that way. But seeing it in action, I think will start making a little bit of sense to you. So here we have x squared plus 4x is greater than or equal to 5x plus 6. For this test point method, we want to move everything from the right-hand side over to the left-hand side. And because we're just adding and subtracting, we're not going to flip the symbol at all at this point. We're going to subtract 5x from both sides, and we're going to subtract 6 from both sides. And ultimately, we end up getting x squared minus x minus 6 is greater than or equal to 0. Step 1, done. Step 2, we're going to factor the left-hand side. So we end up with x plus 2 times x plus 3. Now keep in mind, we're looking for something that's greater than or equal to 0. Step 3, We're going to draw our number line and we're going to solve each individual like we normally would. So for the x plus 2 equals 0, we get x equals negative 2. This is going to be one of our critical points. X minus 3 equals 0, well, that means x equals 3. 3 is going to be a critical value. That means we have divided up this number line into 3 regions. Anything below another negative 2, the values between negative 2 and 3, and the values above 3. The value at negative 2 is a critical point, and the value at 3 is a critical point. But we're looking for the regions. To find the test points, we will just choose something in each region. One in region 1, one in region 2, and another point in region 3. So these are our 3 intervals that we're going to choose test points from. Now that we have our test points, well, negative 3 is definitely in that blue region. So we're going to throw it into our equation. It ends up negative 3 plus 2 is negative 1. That's a negative value. Negative 3 minus 3 is negative 6. That's also a negative value. Negative times negative, and I don't care what the values are, I only care about the signs. Negative times negative is positive. Now, taking a value from the purple region, I'm just going to take 0. 0 plus 2 is positive, right? It's positive 2. 0 minus 3 is negative, and a positive times a negative results in a negative value. I don't care what that value is, it just results in a negative. Let's take, in the orange region, we'll take 4. As long as it's in that region, I don't care what value it is. I could have taken 1,000,000. It was in there. I chose 4. 4 plus 2 is positive. I don't care that it's 6. I just care that it's positive. 4 minus 3 is positive. Yes, it's a 1, but I don't care. I just care that it's positive. Positive times positive is the result is positive. So let's label our number line with positive in the blue region, negatives with the purple region, and positives with the orange region. And here's what it looks like. All of these test values, doesn't matter what I took, would all result in positives. In the middle would be all negatives, and on the right would be positives. Now remember, we're looking where this value is positive, greater than or equal to 0. We're looking for any value of x that made that greater than 0. So let me go backwards just for a second. Here's greater than 0. Here's greater than 0. This is 0. So here is our result. This is a good region, not good region. And therefore my answer is including negative 2 to negative infinity, including 3 to positive infinity, and therefore my solution set looks like this. Let's take a look at our point technique when we have a rational inequality. Oh yeah, a fraction on one side, which just looks to be a mess, but just hang in there. We're going to use those same steps to solve this inequality. First step I'm going to want to do is I need to set this equal to 0. So I need to move this 3 over to the left-hand side by subtracting 3 from both sides. Now I want this all to be one rational inequality. I need this to be one fraction. So I'm going to find common denominator, which will be x minus 1. Multiply both top and bottom of this 3 with x minus 1. And I can combine it into one big fraction now. I'm going to distribute the negative 3 to the x and the negative 3 to the negative 1. Combining like terms in the numerator, I get x squared minus x minus 12 all over x minus 1 is greater than or equal to 0. I want to factor that numerator. The denominator is already factored, so I'm going to leave the denominator alone, but I want to factor the numerator. All right. So now that I factored the numerator, there we go, I get my key points. My critical points are going to be when x plus 3 equals 0, I get x equals negative 3. When x minus 4 equals 0, I get x equals to 4. And keep in mind, x minus 1 equals 0 would give me 1, but I can't include 1 because 1 would make the denominator 0. So I'm going to put an open dot and not include 1 where the denominator value is. So here's what I've got. I've got 1, 2, 3, 4 regions, which makes me have to test 4 points. 1 to the left of negative 3, 1 in between negative 3 and 1, 1 in between 1 and 4, and 1 to the right of 4. As long as it's in region 1, 2, 3, and 4, it doesn't matter what value you choose. I will have to say, anytime I get to pick 0, makes our math a lot easier. So I like having 0 there as my value. All right, so here we go. These are the values I'm going to choose. In the blue region, I'm just going to choose negative 4. When you plug in negative 4 into your equation, or your inequality, negative 4 plus 3 is a negative value. Negative 4 minus 4 is a negative value. Negative 4 minus 1 is a negative value. And these two negatives cancel out, leaving me a result of negative. Okay. Now in the interval of negative 3 to 1, 0 is available, and I love 0. Just makes math easy. 0 plus 3 is positive. 0 minus 4 is negative. 0 minus 1 is negative 1, is negative. And negative over negative is positive, and positive times positive is a positive. Let's look at our next test interval. Between 1 and 4, I'm going to take any value. I chose 2. You can choose any one in there. If you want 3, you can test 3. 2 plus 3 is 5, which is positive. 2 minus 4 is negative 2, so it's negative. 2 minus 1 is positive. So I have positive times negative is a negative divided by a positive is negative. The whole thing's going to be negative in this region. Last region that we need to test. I'm just going to choose 5. You could have chose 10, 100, whatever you wanted to do. I chose 5. 5 plus 3, positive 8, positive. 5 plus 3 is 8, which is positive. 5 minus 4 is 1, which is positive. 5 minus 1 is 4, is positive. So all of these positive stays positive. Looking at our number line, here's what we got. Let me go back. I had negative, positive, negative, positive. So in region 1, all of it is negative. Region 2, positive. Region 3, negative. And region 4, positive. Keeping in mind that 1 is undefined, and that should be an open circle and not included in your final answer. Has to be a parenthesis there, not a bracket if it includes 1. Okay, here's a good region because ultimately I want it greater than or equal to 0. So here's my good region. Here's my good region. And here I'm not including 1. Okay. Negative 3, including, all the way up to 1, not including, including 4, all the way up to positive infinity. So we have a region, and we have, hey, go off to infinity. Here is our solution. All right, we made it to the end of this lesson. We dealt with inequalities, rational inequalities, and using the point test method to find our solutions. So until next time, be seeing you.